All right, let's use implicit differentiation to find the equation of a tangent line. Okay, in example 3, the graph of x cubed plus y cubed equals 9xy shown below is called a folium of Descartes. Okay, Descartes, famous mathematician. Okay, find the equation of the tangent line at the point 2, 4. So a little bit of a picture going here, 2, 4. We see this location touching the graph right there. We can find the equation of a tangent line. Now, something that might be standing out to you right now is just looking at the shape of this graph, that fails the vertical line test over and over and over, right? That's not a function. This is not a function of x because it fails the vertical line test, especially since if I just picked an x value of 2, there's several different spots for y values that match up to an x value of 2. So anyways, this is not a function of x. But like I said, it's almost like we're doing loophole type stuff, because if we look at this function here, or if we look at this graph here, and if we just kind of restrict ourselves to looking at just like a region around that area and only consider the graph right in that region, then we do have a little section that we could consider to be the graph of a function of x. Okay, so it's this graph or this equation right here, that is not a function of x. But if we want to find the tangent line, we can, okay? Especially if we want to specifically find it at the point 2, 4. Okay, so let's find the derivative because the derivative gives us the slope of the tangent line. Okay, so here we go. Find the derivative. We want dy dx. So let's go d over dx on both sides of this x cubed plus y cubed equals d over dx of 9xy. Okay, so if we find the derivative, that will be able to give us the slope of the tangent line. So let's go through and do this. So d over dx, so the derivative with respect to x, that's just a sum of two different things. So the derivative of x cubed, that's going to be 3x squared by the power rule. And then plus, okay, so this one, don't forget the chain rule. So do the derivative like you normally would with 3y squared power rule. But since we're assuming that y is a function of x, times dy dx. Okay, don't forget that chain rule. Okay, equals. On the right-hand side, don't forget, that's a product rule. Okay, so I'm going to think of, how about the 9x separately from the y? Okay, so product rule. First, times the derivative of the second, so the derivative of y with respect to x is just literally dy dx. Okay, so it's like 1 and then the chain rule. Okay, so first times derivative of the second plus the second times the derivative of the first. So the derivative of 9x with respect to x is a 9. Okay, so let's clean this up and try to get anything with a dy dx in it on one side and anything with the dy dx not in it on the other. And again, I always like to go to get the dy dx on the left-hand side. So I'll do that kind of in the same step. Let's go minus 9x dy dx minus 9x dy dx. So we get rid of it on this side. And then I need to get rid of this one from that side. Okay, so then over here, we're going to get 3y squared dy dx minus 9x dy dx equals, and then over here, it looks like we got, I can write that as 9y minus 3x squared. Okay, not too bad. Let's factor out that dy dx. And we have 3y squared minus 9x. And divide both sides by this junk. And we have an expression for dy dx Okay, so for that expression, I am noticing that we could factor out a 3 as a GCF from the numerator and denominator. So I'll probably do that just as I write this down. So how about 3 times 3y minus x squared, factor out a 3, and we get y squared minus 3x. Okay, and then I can cancel both of those, and I'm going to need to have some space here because we still need to find that tangent line. That was an ugly arrow. There we go. Okay, so we have dy dx equals 3y minus x squared over y squared minus 3x. Okay, so we've got dy dx. Okay, so the derivative gives us the slope of the tangent line wherever we want. Okay, and since we've got x's and y's involved, we do need to have an x and a y to plug in. So we were given this point, x comma y. Okay, so we want to find the slope of the tangent line in the derivative here by letting x equal 2 and letting y equal 4. Okay, so here we go. I'm just going to write it as like m for the slope of the tangent line. So let's plug in 3 times y, which is now 3 times 4 minus x squared over y squared minus 3 times x. Okay, and let's see, what do we get? 12 minus 4 over 16 minus 6. And so it looks like we're going to get 8 over 10, which is 4/5. There's the slope. Okay. And then the same process that we would do if we were trying to find the equation of any tangent line, you need or any line, remember you need a point and a slope. Okay, well, we already have our point, and then we have our slope. So to proceed to find the equation of the tangent line, we've done this a lot in the past. Let's plug it into y minus y1 equals m times x minus x1. So we've got y minus, and the y1 is 4 from that point, equals 4/5 times x minus 2, right? 2 from that point. Yep. Okay, and then distribute that 4/5 in there. I'm going to continue the work right here. So we have y minus 4 equals 4/5 x. So 4/5 times negative 2. Looks like we're just going to have minus 8/5. Okay, and then let's add 4 to both sides, and we will be done. Y equals 4/5 x. Okay, so how do you deal with that? Negative 8/5 plus, okay, 4 over 1, it's got to be 20 over 5 for a common denominator. So this is just my scratch work, so I don't have to use a calculator. So that's going to be 12 over 5. Okay, so we got 4/5 and then plus 12 over 5. And here is the answer. So awesome to be able to find out the equation of that tangent line, because this was not even a function technically, but if we just kind of restricted our region and the little region around the point of interest, then we can use implicit differentiation to find out a derivative that gives us the slope of the tangent line. And then we're able to find out the tangent line itself at that moment. So pretty awesome stuff. I think it's just, calculus is just so amazing what it can do. Okay, so speaking of what it can do, in the next video, we'll look at some applications of implicit differentiation.